welcome everyone to Cohere for AI. We have an exciting session today with two exciting guest speakers. And with that being the case, before starting, for those of you who are new, just wanted to give you an overview of Cohere for AI. Cohere for AI is a hybrid research lab and open research community dedicated to contributing fundamental research in machine learning. And Cohere for AI works to solve some of the field's most challenging problems. And one of the most important aspects, or one of the most important missions of Cohere for AI is it creates more points of entry into machine learning research. And one of the more important ways that we do that at Cohere for AI is with guest sessions or guest speaker sessions like we have today. So our guest speaker session today, we have two exciting speakers. We have Romain Loiseau, and we have Elliot Vincent. Romain completed his PhD at École de Pont, working with the Imagine team and the French mapping agency, IGN. And Romain's research focuses on optimization and machine learning for 3D data, with a special emphasis on unsupervised learning, interpretability, and real-time applications. Elliot Vincent is an AI engineer and a researcher at the French mapping agency IGN, and his research focuses on machine learning and computer vision for remote sensing, particularly, as we'll discover today, satellite image time series analysis for tasks such as land use classification and change detection. So with that being the case, with no further ado, I'm going to go ahead and hand off to our two guest speakers today.
Thanks a lot, Ahmed and Elliot. If you want to give a few words about IGN. During this time, I will share my slides.
So, IGN is a public French institute in charge of the mapping of the territory. So one of the main tasks of IGN is to map the French territory and to detect a change happening on this territory. So with different products being maps at the resolution of 20 centimeters per pixel, but also 3D representation of the territory. And IGN also have its own research lab in which Romain has done his PhD.
Yes, so thank you, Elliot. So, and as you will see, so Elliot is now at the IGN, and I did my PhD at the IGN, and we really benefit from both the expertise of more computer vision oriented teams, such as Imagine, in which we both did our PhD, and the data and yes, from and the institute where the data is acquired at IGN. And so this is basically the context of the project, and we'll try to explain it and to detail it for during this session. So thanks a lot for inviting us. So today we'll present our paper, Learnable Earth Parser, Discovering 3D Prototypes in Aerial Scans. I will first give a small introduction, then Elliot will detail the methodological work which this work is based on, and then we'll dive a bit more into the details of this very specific method. So the goal of the paper is to design a method that can take large aerial 3D scans as input and perform semantic segmentations and instance segmentation without any supervision. When you look at prior works, they often need very large annotations for basically supervised semantic segmentation. They can have very low interpretability, and if they work, it's very difficult to make them work on real-world 3D data. And they often work very well on toy scenes, on objects, but very well. It can be much more difficult with real-world 3D data. Our contribution works without any annotations, and is based on the learning of 3D prototypes that are used for reconstruction. And through this reconstruction, we get semantic segmentation and instance segmentation. So the only supervision is a reconstruction loss, and it works on real world data. So so we present both. So in this paper, we present both a method, the Learnable Earth Parser, which is an unsupervised framework to parse those large real-world 2D scans, and the Earth Parser dataset, which is a new aerial LiDAR dataset with annotations in various environments. So this is basically what we want to do. We want to design a method that can parse 3D scans. 3D scans to perform semantic segmentations and intent segmentation. What we will do is learn 3D prototypes that will be used for reconstruction. So what we will ask our model, what we will ask our model is to reconstruct the scene using only a very few number of prototypes, basically between 3 and 6 prototypes that can be deformed to reconstruct an input scene. And what we hope is that once we learned meaningful prototypes, we can just look at them at a glance, annotate them, and then project the semantic segmentation and the instance segmentation onto the input scene. So as you can guess, it's pretty challenging for mainly 2 reasons. First of all, because we have a huge diversity of objects. So in those large aerial 3D scans, there can be very different types of objects, and we want to learn the objects composing the scene without any supervisions. And also the object separation can be ambiguous, and splitting between object instances can be pretty difficult. We can also have a varying number of objects in one scene, which is not the case when you work at object level. So to assess our method, we introduced, as I said, the Earth Parser dataset, which is an annotated aerial LiDAR scan dataset acquired in very diverse environments. So it's data part of an IGN program, LiDAR HD, which aims at acquiring a full 3D model of the French territory with roughly 20 points per meter squared. So I think the acquisitions are nearly complete, or they will be completed in the end of 2020. Well, during 2025. So basically, we took some of those scenes, and we wanted for those scenes to be as diverse as they could to assess that the performances of our model on such scenes. So we have wind turbines, the forest where we have lots of instances of trees. The crop field is pretty easy; it's basically ground. The urban scene is very difficult to understand and to represent with a very few number of prototypes. On the power plant scene, you can see here, but we have lots of lines which are running through the scene, and they are very difficult to parse, and greenhouses and a marina. So basically, we tried to get as much diversity as we could to assess our method. So as I said, we designed a method which is decomposing a full 3D input using a very small number of prototypes for reconstruction and a data set in this paper. But before digging into the details of the paper, I will let Elliot present the framework in which the paper comes to.
Yes, so the idea here is to make sure you understand the deep transformation invariant clustering, which is really at the core of the paper we present today. So we'll see how it works with the toy example. Imagine we want to cluster a set of images like this, which we're interested in the shapes, but we know a priori that the color and the size of the objects in the image is irrelevant. And we have also additional constraints. First, we want to have a fully unsupervised methods, and we don't want to use trained features. On the one hand, supervised features require annotation that we do not have, and self-supervised feature requires a lot of data. We also do not want to use handcrafted complicated features because we have a high priority on simplicity and interpretability. For this reason, the method we are looking at is doing clustering in the input space. So a very basic and common method to do clustering in the pixel space is k-means. And so the idea is to make to compute the Euclidean distance, the pixel-wise Euclidean distance between cluster centroids and the images. But if we do this with the set of images, we will most likely end up with clusters grouping the images with respect to their color, which we know is irrelevant for the task here. We could get rid of the colors and do the clustering in grayscale, for example, but in this case, we would most likely end up with cluster grouping the images with respect to their size, which we also know is irrelevant. So what we want to do is design a method that is transformation invariant, which means it's invariant to color transformation on the one hand and scale transformation on the other hand. So the prototypes we will have will typically look like encode the shape information of object we're interested in. So how do we do this? We have a set of 3 prototypes and an image that we want to cluster. We dispose of a function f parameterized by theta, that is in our case typically a neural network, and theta are the weights of the neural network, and it outputs color parameters that we feed to a transformation module that will color the prototypes that we have. The same function outputs scale parameters that again we feed to a scaling transformation module that will again transform the prototype. With this method, we have as parameters the prototypes themselves, but also the parameters, the weights, theta of the neural network. They are learned by minimizing a loss, a reconstruction loss, that compute the difference between the input image X, and its closest transform prototype. So this is the basic framework of DTI clustering. Do not hesitate if you have questions at this point, because it's important to understand this pipeline. And this gives us a recipe to apply DTI clustering to a collection or a dataset. So as a proof of concept, we first use DTI clustering on datasets of digits like MNIST or SVHN by designing simple spatial, morphological, or color transformation and using as the transformation parameters encoder a simple ResNet. The main output of DTI clustering are the learned prototypes, which in this case are the digits from 0 to 9. Then several papers on which either Romain or I have worked on use DTI clustering in other frameworks. In this case, we needed to add a layered composition transformation in order to account for the presence of multiple objects of the same class in the image, and to compose an image as a layer of different sprites. In another work, we design transformations specific to audio data. For example, transformation on the gain or the pitch of audio, or filters on the low or high filters for high frequency filters. In this case, the prototypes are actually audio samples that you can actually listen to and that represent different types of instruments or voices. So you have also 2 additional works. The first one is applying DTI clustering to satellite image time series, and in this case, both the parameters prediction network and the transformation are specific to temporal data, with a time warping and an offset transformation, which we applied to agricultural classification. In this case, the prototypes are time series specific to a type of crop like wheat or barley. And also we use DTI on ancient documents in order to discover alphabets. And finally, this recipe can also be applied to 3D data and to large collection of 2D shapes, or to discover 3D shapes in RL scans. And it is what Romain is going to talk about now.
Yes, thanks a lot, Elliot. So as you understood, all the work I will present now is based on this idea that we want basically to learn from large shape collections, prototypes, alongside ways to deform them and to position or transform them to represent a collection of shape, 3D shape in this case. But as you can see, as Elliot explained, it can be applied to lots of other modalities. So as I said, we have two main challenges in our paper Learnable or Parser. The first one is dealing with the diversity of objects we see in the scene, and the other one is dealing with the variable number of objects in one scene. So let's try to focus on what happens when we have only one object in the scene. So the goal here is to go from n objects without any labels to k groups semantically homogeneous. Here we have only one object in the scene, and basically what we'll do is to perform unsupervised clustering in input space, and our goal is to have as output, learned from the model 3D prototypes that we can visualize and which we can understand the transformations that have been applied on them to reconstruct all the diversity of input shapes. So what do we need for to perform k-means for point clouds? First, we need inputs. So in this paper, we used the ABC and ShapeNet. So the first one being a large unannotated collection of industrial objects. The second one being a large collection of annotated shapes of day life, so chairs, airplanes, cars, etc. So all those inputs can have a variable number of input points, but our method won't be a problem for our method. Then we need a distance. We need a way to compute the distance between two objects. So here we use a 3D distance, which is the Cohere distance. So it's a symmetrical distance, which for each point of each point cloud computes the distance from this point to the closest point in the other point cloud. And so this is a standard distance we use in 3D to compare 3D shapes. And then, so if we wanted to do only k-means, we would need a way to average point clouds to perform the centroid update step. But as Elliot explained, we cannot average either images, but we cannot average point clouds neither. And this is why we use the gradient-based k-means for point clouds. So here, what we'll do is optimize directly the prototype's coordinates. So here, our loss is for all the shapes in the data set, the Cohere distance between the input shape and the prototypes that reconstruct best the given input shape. Here you can see that it works. You can distinguish the chair, the table, the toilet here. But you can see that our prototypes are super fuzzy. They are super fuzzy because our Cohere distance do not model the 3D transformations. Here, for example, we would need we would want the distance between all of those chairs to be 0. They are the same chair, just rotated. However, our loss does not model the transformation. So, inspiring from the deep transformation invariant clustering Elliot presented, we learn a way to align prototypes to input. So here we learn alongside the prototypes a neural network which takes an input shape and outputs a rotation and a translation. Doing so, each prototype will learn to align itself to a given shape. This way, we can minimize for each input shape the chamfer distance between the input shape and the closest prototype, the prototype that reconstructs best the input shape regarding to a transformation predicted by a neural network. Here you can see that our prototypes are much more sharp. They represent better the shapes contained in the dataset. However, you can see that they are still fuzzy. For example, here the chair, we do not know if the chair has armrest or not. It's difficult to understand what's under the table, and this is because 3D shapes require shape-dependent deformation. For example, a chair can have armrests or not. An airplane can have a variable number of motors, and etc. To model those shape-dependent deformations, we inspire from an idea from an old ICCV paper, which introduces linear shape modeling. Here, we basically learn to generate images from an average face image and component and noise deviations. Here, we'll do the same. For each point of each prototype, we learn displacement directions, points alongside which they can move, directions alongside which points can move to deform the objects. And so we learn those displacement fields for each individual prototypes, and we'll predict displacement intensities. So how much do we need to apply this displacement field for each point of the prototype? So for a given prototype here, for a given centroid here, we will learn to deform the centroid alongside different directions to move continuously from a jet, an airliner, and or a military plane, for example. Here you can see that our shapes represent way better the diversity of shapes contained in the dataset. Because, for example, here the armchair can go on the chair or model the armchair more truly. So this is basically our framework. Using the framework, we can do very easily unsupervised clustering with a single reconstruction loss. And this enables us to visualize large shape collections and to organize large shape collections with a very small amount of learned prototypes. And here you can see that each prototype can represent a diversity of existing 3D shapes. But we can do better. Because our prototypes can be visualized, we can very easily, by just looking at them, annotate them manually, and then propagating the labels from the shape, from the deformed prototype to the input shape, just by looking at the closest point of the prototype for each point of the input and propagating the label. Doing so, we show the state-of-the-art performances for few-shot semantic segmentation. So okay, so now you have the full overview of the prior work. With this paper from 2021, we presented an unsupervised method to represent large point cloud collections. And it's really an extension of the deep transformation invariant clustering framework Elliot presented, which learns linear shape models directly in 3D. It produces viewable representations in input space and state-of-the-art few-shot semantic segmentation performance. Okay, so now let's get back at our large aerial 3D scans. So I think now you can guess a bit what will happen. We tackled the diversity of objects, so we know that we can learn prototypes from large shape collections that can represent well the diversity of objects contained in a big data set. We showed that we can do very easily semantic segmentation with it, but now we want to deal with a scene that have varying number of objects inside and which we don't know the object separation. So we'll do a bit the same. We'll try to learn prototypes and to learn a way to deform the prototype to perform reconstruction. The thing is that here we'll need to use multiple instances of each prototype to reconstruct our input scene. Okay, so let's represent the problem a bit differently. So we have here an input. We will learn 3D prototypes, and we have a reconstruction here. Let's see how we extend this framework to multiple objects in the scene. So what we do is basically we will reproduce the mechanism as time. So we use slot models, and what we'll expect is for each slot to model, to reconstruct only one object from the input scene. So here, each of the slot will have to reconstruct individual objects from the scene. Our final model is just the union for all slots of slots outputs. Here we do the same. We learn to deform the different prototypes using an affine transform, and the case output of the slot model S is the transformed is the prototype K transformed depending on the input and a slot-wise transformation. If we do so, our model will be able to reconstruct scenes with only S objects. So we need to learn a way to activate or deactivate our slots. Here, we predict also with the same function, we predict a slot activation alpha S. Now, what we have is a probabilistic reconstruction model, which we can sample depending on the alpha S. Now, our final reconstruction is the union for all activated slots of the outputs of the slot model S. Now we can deal with varying number of objects in the scene. We also need a way to choose the prototype being used in a given slot. So we also predict betas from 1 to k for each slot S, and we can sample in this probability distribution. We can sample to our model to perform the reconstruction. So now each slot is equipped with an affine transformation module, an activation module, and a prototype choice module to deform the prototypes, select the prototype to be used at a given slot, and then activate or not the slot. So here you can see that in the image all the slots are activated, but we can imagine scenes in which it's not the case. So we explained before that it works. We can learn such model, but how can we learn alongside the prototypes, the deformations, and the activations probability? What we'll do is a bit the same. We'll extend the chamfer distance to reconstructions using different to reconstruction using multiple number of prototypes, and to probabilistic reconstruction, because here what we predict are probabilities. So first we want to maximize the accuracy of the reconstruction. So we'll minimize the expected distance between activated slots and input points. So basically we'll ensure that each point from a probable slot is close to a point from the input. And we'll also ensure coverage. We'll ensure that each point from the input is close to at least one point from an expected slot. In the end, our loss is the combination of a reconstruction loss here, probabilistic reconstruction loss, and regularizations to ensure that we use as minimum slots, that we activate as minimum slots as we can to reconstruct the input, and two losses ensuring that we use evenly all the slots and prototypes. So let's look at real data now. On those 4 scenes, you can see that we learned very different prototypes depending on the scene. So you can clearly distinguish here the wind turbine, and here the mast and the boat and the hull of the boat. You can see that those prototypes are super easy to annotate. You can just look at them, annotate them, and once you have annotated them and you can and that you reconstructed the input scene, you can very easily project the reconstruction, project the annotation from the reconstruction to the input. This way, you can perform semantic segmentation very easily, and instant segmentation because you can retrieve which prototype has been used to reconstruct which part of the scene. This way you can well perform semantic segmentation for free on large real-world 3D scenes and perform instant segmentation also, so count objects. For example, here boats in a marina, wind turbines, or trees, for example. So let's see a bit how the performances regarding to other ones. So sorry, I'm reading a question. How does the method determines determines the optimal number of prototype for each scene? So yes, so you're right. Here we work at fixed number of prototypes. So yes, so here we work with a fixed number of prototypes and a fixed number of slots. So as I said, we have regularization losses, ensuring that we use evenly all the slots and prototypes to ensure that we do not that all the information is used by the model is useful. However, we also use we also have a way to remove useless prototypes. For example, if you have two prototypes representing the same types of objects and that are not when keeping only one makes more sense, we have a way to remove useless prototypes. So it's pretty easy. It's really after training, once everything has been learned, we can remove prototypes individually. In the experiments, we used a fixed number of prototypes for all the experiments. So we didn't fine tune the prototypes, the number of prototypes we use for each scene. However, we could see that the number of kept prototype in the end are not the same for all the scenes, because some scenes might require a very large number of prototypes because of the diversity of objects, where other can, for example, the tree, a forest with lots of times the same trees, 2 or 3 prototypes can be enough. So I don't know if it answers your question, but
yes, it did. Thank you.
So let's look at some quantitative results. So here you can see two scenes. So our power plant and a urban scene, and you can see the input RGB and the intensity, so the intensity return of the LiDAR. So first, let's do something very basic. We just perform a k-means regarding to the intensity, return intensity of the LiDAR, and the altitude. You can see that we get pretty decent performances using this method. So it's a very basic method. So it can work. However, it won't work if you have well, depending on the type of objects. And for example, here in the urban scene, you can see that just looking at the altitude won't give much information. However, it still works a bit, but it does not provide a reconstruction. It's not interpretable. I mean, the sound grids are not interpretable, and it cannot perform instant segmentation. We also compared with another method, which is close to ours, but instead of using a collection of prototypes, it uses shapes from the superquadrix family, which is a family of continuous of shapes you can deform continuously. It gives good results in reconstruction, and here I don't know if you can see it well, but basically you can see that it reconstructed successfully the different lines from the power plant. However, it tells nothing about the scene. We do not get semantic information, neither instance information. We also try to extend the 2D ideas Elliot presented. working in 2.5D, basically having 2D projection of our input scene and learning depth prototypes to reconstruct. You can see that it does not work very well because of mostly because of the density of points, which is difficult to manage using images. However, it gives chamfer and it gives a reconstruction error and instance information, instance and semantic information. The last one is AtlasNet v2. So it's a method which is comparable to ours, but it chooses as much slot as prototypes, and the slot S has to be assigned, has to activate the prototype K. Basically, it can only use all the prototypes and one time only. So you see that it gives, well, different reconstruction performances, but the instance segmentation is meaningless because the model have to use all the prototypes and cannot parse between the diversity of objects composing the scene. Our model finally can decide which prototypes have to be used for which scenes, and you can see here some of the reconstructions. It gives very good results both in reconstruction and in semantic segmentation. Well, I said very good results in reconstruction. It's better results than others. Here you can see that the reconstructions are not good. You would not want our model to perform accurate reconstruction. I mean, this is very easily understandable. We used only a very few number of prototypes, between 4 and 6 prototypes, to reconstruct a full scene, and the transformations we had are only rotations, translations, and a bit of other deformations, but they are very small transformations, which explains why the reconstructions are not perfect. However, it gives very good semantic segmentation and instance segmentation performance. So in the end, we presented a method, an unsupervised method for parsing complex real-world aerial 3D scans in simple parts, which produces a viewable and interpretable representations of input space and in input space. It gives a state-of-the-art semantic segmentation performance for unsupervised clustering, and so the paper was published at CVPR this year. So thanks for your attention. I don't know if you have questions. We'll be glad to take them with Elliot.
Okay, thank you so much. I'm looking in the chat to see if there are any additional questions. I'll go ahead and place a question in the chat. I had another question, at least in terms of future usage,
Yes.
and it might be easier just to place it in the chat. So I'll put another question in the chat.
For other 3D sensing technologies beyond LiDAR, such as photogrammetry or radar. So the idea is a bit the same each time, basically. You want to have a way to define inputs. So these are basically 3D data or images or audio, as Elliot said. A distance between inputs, sorry. So here we use the chamfer distance. We could have used other types of methods, but chamfer distance is good for 3D. And then you need meaningful transformations in input space. For example, rotating a 3D object is meaningful. So then you can do pretty much whatever you want using those 3 basic principles, and the method can really be derived for all of those different modalities. So basically, Elliot showed a good example of this method on a satellite image time series, and to explain to cluster between the different crop types, and so it works the same.
Oh, okay. So this can be used outside of Earth-based observation, can be used with satellites as well.
Yes. So for example, in this work. So I don't know if Elliot, you want to give a bit of insight about this work.
Yes. So here, like, the data is different. We are looking at multivariate time series. So it's a pixel-wise method. But because we are working with time series, we need to adapt the encoder and the transformation to the specific task. But the key idea of representing a collection of pixel-wise time series with a very small set of prototypes is the same.
Okay. So I'm curious, looking far in the future, or maybe the way that AI is going, maybe not that far in the future, or machine learning. But have you guys thought about future applications for real-time 3D parsing? I know it would be somewhat difficult with the current technology, but is there possibilities that a variation of this method could be used for real-time 3D parsing of LiDAR?
Yes, so this is a question we had. So we didn't implement it so far, but using, for example, rotating velodynes, which are acquiring 3D data in real time for autonomous driving applications, for example. And here the difficult thing would be that we would have to manage spatio-temporal prototypes. And I have no good ideas about how it will work. The second difficult thing would be managing occlusions. I don't know if you already use such data, but often when you deal with real-time 3D acquisitions, you have occlusions problem where you will, for example, acquire only one side of a car in outside environments. So this would be the two main problems. So first, the temporal aspect of the data, and then the fact that you want to, if you want to learn meaningful prototypes, you do not want for your prototypes to model the occlusions. Basically, you would want a one prototype representing a car being able to reconstruct a side, the acquired side of the car, for example. So yes, there. For each of the different problems we showed and Elliot showed, there are very specific aspects of the data we need to manage, and for example, so as we said, we derived the work for audio data. Here we had the chance to be associated with guys from another lab, which are really from the audio world. And they could really help us, looking at the data, getting good insights about which data, which transformations are the most representative of transformations of the data in the real world. So short answer, it can be applied. It can be difficult because of the data, yes, because of specific data aspects.
Okay. I see, Mayank, I see your question's been answered. Did you have any other questions, Mayank, that you wanted to clarify? It looks like your question was answered earlier, though.
Yeah. So regarding the boat instant segmentation diagram, so like you have a couple of things like there. You guys calculated the mean relative error that gave the predictions to the number of boat-like prototypes in these zones, like the lower right figure that I am talking about. So like, yeah. So so I think so there are sprite methods too. I'm not too sure. Let me take a quick look at the paper. But yeah, yeah. So how was it better than their approach, or like how did you compare here?
So I'm not sure I understood fully your question, but maybe to answer one point, I think you mentioned the fact that we would want to look at the reconstruction error when we have semantic segmentation error, and this we can do on not on unannotated data, and it would be on annotated data, sorry, and it would be very useful to assess whether or not to try to get a confidence level on the semantics depending on the reconstruction, basically. This we didn't do, but it's a very good idea, I think, to look at where the model is bad at reconstructing the input data, and to see if it correlates with the semantic segmentation error. So I think this was the first part of the question, but I'm not sure I fully got the second one.
If I understood,
Oh,
if I
yeah.
understood
Let me try to clarify my query here. So I just opened up the paper, and on page number 8, just below the diagram, you say that your method yields a MRE of 7. That's
Ah.
2.6 times lower than the DTI sprites,
yeah,
demonstrating its strong performance. So that's what I was kind of like getting at.
yeah. So it's for the task of counting the number of boats.
Yeah.
Yeah, so this is for more for an instance segmentation metric. So as you can see in the paper, we have a very detailed metrics regarding semantic segmentation, but we have a very few regarding instance segmentation, because we didn't have annotation. So Elliot had to do it manually on a few selected data portions, and basically we showed that our method has way better instance segmentation performances than others. I don't know
Cool,
if you want to add something, Elliot, but basically here you can see what happens on our tree on our forest. Well, we can clearly see that what's happening is somewhat pretty good.
Mm-hmm. Yeah.
And this is
Plus,
the same for the images in the paper.
Mm-hmm. Yeah. Plus, like my previous comment, like with the interpretable prototypes, and with respect to how your how your prototypes like are being differentiated when the data kind of moves from one distribution to the another. So that's one objective that you handled well too. So like you have a kind of a Bernoulli distribution there, and so those kind of a constrained nature of the deformations like prevented the slots from repurposing kind of like the same prototypes for different objects. So that was my other query. Yeah, thanks.
Thank you.
Okay, so Samir, did you want to come off mute for your question? If you had a little bit more detailed, I asked a little bit about 3D for real-time applications, but I think your question is a little bit a little bit different. Would you like to come off mute? Or do you see Samir's question, Romain?
Yeah, I can see it. So it's about can the model be used for vehicle automation, so for autonomous driving methods typically. To be honest, so I discussed a bit the part regarding temporal aspects, but
Right.
we investigated a bit regarding whether or not it could handle rotating lidar data, and as I said, we have we had lots of issues regarding occlusions in this kind of data. So, however, well, so I think the method can be used, but it's a bit what I said already. Is we have to find the way to represent the data as well, to represent the physical aspect of the data as good as we can in order to do something meaningful, basically.
Okay.
And managing occlusions means doing something differently in the chamfer distance, for example, which we didn't find the good way to do it.
Okay, thank you. I may. I was just asking if it will be able to process the surroundings of the vehicle, since it will be in some setups necessary to use segmentation to understand what's out there, and for the vehicle to be moving well around on the path. So yeah, I think occlusions and having the speed to just be able to respond in real time will be a obstacle.
So then the second thing is that you are right here. We overfit our model on each of the different scenes. So this is the first important thing. So each prototypes are learned independently for each scene. We showed in an ablation that if you take a scene which is looking a bit the same as one from our data set, you can perform you can reconstruct with the same reconstruction and instance segmentation performances. So this is something good. However, in a difficult urban environment, I'm not sure about how it would manage it if you would just want to perform to reconstruct full 3D rotation, full rotations of the 3D sensor at rotation speed. I think it's something like 10 Hertz in a standard autonomous driving applications. So I'm not sure it will handle the real-time acquisition.
Okay, thanks.
So I just wanted to ask one more quick question, at least in terms of the data set. So I know I was reading a little bit about IGN, and I know the plan for IGN was to cover the entire French territories by the end of 2024.
Yeah.
So does the data set have that latest data, or what is the latest update on the Earth Parser data set?
Yes, so I'll give a few words, and then Elliot, you can complete. But basically, we took the data from the time which we did the data set, so it should be something like 2023.
Okay.
The French coverage from the IGN in like using LiDAR, so it's a full coverage using with the acquisition with roughly 20 points per meter square, so it's super dense. But we have only one acquisition. It's not meant to be updated, or at least it wasn't when I left the IGN. So I don't know, Elliot, if you have more insights.
So on the one hand, we have the Earth Parser dataset that is as it is now and is not meant to become bigger.
Okay.
And it was meant like for the application of GTI in large RL scans.
Okay.
But actually, IGN produced LiDAR HD, which is the name of the product at the entire French scale. And this will be released in open access by the end of next year, I think. And actually, I think anyone can download a tile of this LiDAR HD and apply the Learnable parser on this tile. But like here we have taken some tiles that we deemed interesting and have created them and put them in the form in which machine learning scientists and a researcher could use it easily.
Okay.
Yeah.
And will LiDAR HD be the entire French territories, or will that mainly be major urban areas in France?
No, it's the entire French territory and
wow.
ultramarine territory as well.
Wow, that's interesting. Okay, alrighty. Okay.
If I may, I think the LiDAR HD dataset is fully annotated with at least semantics.
Oh,
Yes,
really?
it's a basic semantic classes like vegetation, ground, and impervious surfaces.
Interesting. Wow. Okay. Were there any other questions for Romain and Elliot before we ended our session today? Okay, well, we appreciate your time, Romain and Elliot. This was actually a really interesting session. And with the LiDAR HD information that's now available, or will soon be available by the end of 2024, it might be interesting to have you guys come back for a future session.
Thanks a lot.
Okay.
And thanks a lot for having invited us.
Okay, you're welcome. Well, thank you again. And everyone have a great rest of your day or evening.
Thank you as well.
All right,
Bye.
bye-bye.
Thanks, folks. Take care. Bye.